Now I'd like to switch gears and start talking about temperature. Temperature, like pressure, can also be expressed in a variety of ways. For example, we can talk about temperature in degrees Fahrenheit or degrees Celsius. We can also speak of it in degrees Kelvin and Rankine. I'm sure all of you are familiar with the Fahrenheit and Celsius scale, but you may be puzzled, well, what is degrees Kelvin and Rankine? Temperature expressed as Kelvin and Rankine is referred to as absolute temperature. Pressure, as you noticed earlier, can also be expressed as gauge pressure or absolute pressure. And the same is true for temperature. We can talk about absolute temperature. So let's pause for just a moment and consider this concept of temperature a little more closely. What exactly is temperature? Well, temperature, in its most fundamental sense, is really a measure of kinetic energy. And on the absolute scale, 0 is that point where all kinetic energy is gone. In other words, there is no molecular movement whatsoever. So that is 0 in the absolute scale. The only movement that remains is the silent spin of the electron. Now, in clinical practice, temperature will oftentimes vary every time we put a person in the hyperbaric chamber. And it's important to understand this. So let's take a little closer look at what's happening for a patient. If we look at 1 cubic foot of gas, it has a certain amount of energy. Now, if we take that energy and we compress it into half the space, then you're going to have twice the amount of energy present, because we're taking this large amount of energy and compressing it into a very tiny space. We're concentrating it. So what happens is the temperature rises. Now, this is very common when we compress a hyperbaric chamber. If you've ever, for example, pumped up a bicycle and felt the bottom of that bicycle pump, you'll notice it gets hot. If you have a home compressor, you'll notice it has fins, because as we compress the gas, it gets hot. If you have a heating and air conditioning unit, sometimes people refer to that as a heat pump. Why? Well, you're either compressing and moving heat into a building or decompressing and pulling heat out of a building. But this is a very important concept to understand when we talk about temperature, because the first law of thermodynamics is that energy is neither created or destroyed. So if I have 1 cubic foot of gas and I compress it, I am basically concentrating that energy. So I have greater molecular motion within a smaller area. And this is reflected as an increase in temperature. So what do you suppose happens in clinical practice as we compress the patients in the chamber? Well, many of them may start to complain of feeling hot. It doesn't mean that we have to work them up for hyperthyroidism. And likewise, as we complete our treatments and begin to decompress, we're taking the energy, expanding it, diluting it, so to speak, and the temperature will fall. If you run a multiplace, it's particularly dramatic. You can sit at the control console and watch the starting temperature of the chamber rise from 70 degrees to 72 degrees to 75, 76, 77. So this is not a small observation. It's very real, and patients will experience this. Now, in a monoplace chamber, there is a flow of gas through the chamber. In many chambers, this flow may be 300 liters a minute. So why is the flow so high? Is it that the manufacturer is concerned the patient will suffocate? No, they certainly don't need 300 liters of gas. Much of this gas flow is used to cool the chamber. The acrylic wall really doesn't conduct heat very well, and so the patient will experience this rise in temperature. And one way that we can cool the chamber is to increase the gas flow. You might find this clinically useful, particularly if you're in a southern climate, it's already quite hot outside, and you have a really big patient who comes in, and then further consider if they have trouble with confinement anxiety, claustrophobia. There's nothing worse than being hot and stuffy. That's a common expression here in America. And some of these patients just won't tolerate that treatment very well, and they may just stop coming altogether. Well, what can you do? Well, armed with this information that we just discussed, you now know that you can perhaps reach under your chamber, dial up that flow rate, and help to cool it more effectively. This may be sufficient that now your patients are willing to come to HBO because they're a little cooler, a little more relaxed, and they don't feel so hot and stuffy, particularly for our patients with confinement anxiety. So this concept of temperature is really very important to appreciate in the clinical arena. It also is a guide for you so you don't needlessly work people up for hyperthyroidism, and you'll understand what is happening. But there's another reason we need to know about temperature, and particularly absolute temperature. It's so that we can work a few of the other gas laws. So let's take a little closer look at these scales. The Fahrenheit scale is named after the German physicist Gabriel Fahrenheit. And on this scale, the freezing point of water is 32 degrees. It boils at 212, as most of you know. The ignition point of paper is at about Fahrenheit 451. In fact, that particular temperature, Fahrenheit 451, became the name of a very popular novel about burning books. So you're getting to learn a lot of things here in this course, including literature. Well, Fahrenheit came up with this scale in the first place because in 1724, as a scientist, he was looking for that temperature that could be reproduced anywhere in the planet on a consistent basis, because he was looking for a reference point. And he found that in that year, 1724, the one temperature that could be reproduced almost exactly anywhere on the planet was by mixing ice and salt. And so he designated that temperature as 0. Well, based on that scale, water freezes at 32, boils at 212. So now you know the historical roots of the Fahrenheit scale. The Celsius scale, or centigrade scale, was developed by Anders Celsius, and at least in his mind, he felt this was a more rational scale. On this scale, he designated the freezing of water as 0 degrees, boiling at 100 degrees. So how about these absolute scales? Well, the Kelvin scale, named after the Baron Kelvin, is based on temperature expressed in degrees centigrade. And on this scale, centigrade plus 273 will give you degrees Kelvin. On the other hand, the Rankine scale, named after the Scottish engineer William Rankine, is really predicated on degrees Fahrenheit. So if you take your temperature in Fahrenheit and add 460, you will now have degrees Rankine. Now, temperature is important in understanding several other gas laws. One of them here is Charles' law. And what Charles' law states is the volume of a gas varies directly with the absolute temperature. I'm sure many of you know that if you warm up a balloon, it can get larger. If you cool it, it will get smaller. Well, that's Charles' law. Many high school students understand these gas laws, even though they may not know the names of them. For example, most high school students know that you wouldn't take a hot can of Coca-Cola out of the trunk and open it up. Why? Well, it'll blow up. Well, whose law is that? Well, that's actually Charles' law. The volume of that gas is going to try and expand in accordance with the temperature. And a hot can of Coke will have a high gas pressure. Now, that same can of Coke taken out of an ice-cold refrigerator, we don't need to worry that it's going to explode and create problems for us. So that may help you to better appreciate Charles' law in everyday practice. Now we can take Charles' law in this example and put it into play. Let's go back to that balloon we spoke of earlier. 24 cubic feet on the surface of the ocean. What would the volume of that balloon be if we plunged it down to 99 feet? Well, if we go down to 99 feet of seawater, we know that it's a lot colder down at that depth. Starting at the surface, we begin with a surface temperature on the beach with a balmy 80 degrees. At 45 degrees Fahrenheit, which is the temperature at 99 feet, what would the new gas volume be? Well, to come up with that volume, we have to first off consider Boyle's law, which we did earlier, and then we have to apply Charles' law. According to Boyle's law, the balloon should be 6 cubic feet. But when we factor in the temperature change, we find that it's not the predicted 6 cubic feet according to Boyle's law. The actual volume of that balloon, once we adjust it for temperature, is going to be about a half a cubic foot smaller. Remember, to get an absolutely correct answer, we must use everything absolute, both absolute pressure and absolute temperature. In this case, we're using absolute temperature measured on the Rankine scale. So when we convert our starting temperatures, 2 degrees Rankine, we find that the actual volume of the balloon is not 6 cubic feet, as Boyle would have predicted, but it is actually 5.6, almost a half a cubic foot smaller. So that's Charles' law. The next gas law we'll look at is Gay-Lussac's law. Gay-Lussac's law is somewhat similar to Charles' law. However, Gay-Lussac noticed that it's the gas pressure, not volume, but the pressure will vary directly with the absolute temperature. That is to say that if a gas cannot expand, if it is trapped and we warm it, then we will see a rise in pressure as opposed to volume. So let's take Gay-Lussac's law and put it into play. Let's say that we have a scuba tank at 3,000 pounds per square inch gauge. Remember what I said? If you want an absolutely correct answer, you better do everything absolute. So what is the absolute pressure of the scuba tank? Well, it's 3,000 pounds per square inch gauge plus the background pressure of the atmosphere, which is 14.7, which means the pressure in an absolute sense is 3,014.7 pounds per square inch absolute at the starting temperature of 64 degrees. Now, if this scuba tank is left in the sun and the temperature were to rise to 102 degrees, what is the new pressure for the scuba tank? This will be fairly easy to calculate. We will have to take our temperatures and convert them into absolute temperatures so we get an absolutely correct answer. So starting off with pressure absolute, 3,014.7 pounds per square inch. Using our starting temperature of Fahrenheit, we're going to convert into the Rankine scale. If we were given a starting temperature in centigrade or Celsius, then we would convert to the Kelvin scale. So in this case, to convert to Rankine, we add 460. We come out with the degrees Rankine. The rest is fairly simple. We set up the relationship in accordance with Gay-Lussac's law. We take our starting pressure of 3,014.7 and multiply it here basically by this new fraction of 562 Rankine over 524. And we find that the pressure will increase at the higher temperature. The new pressure will be 3,218.6 pounds per square inch gauge. Again, we're expressing our final answer here in gauge. If we wish to express it in atmospheres absolute, it would be 3,233. But remember, the question was, what is the new gauge pressure? Now, all of these concepts can be summarized here in what's known as the general gas law. The general gas law is expressed as P1V1 over T1. and any change in these variables will be reflected on the other side of the equation. So we can look at this in a slightly different way. This diagram will help you better understand the interactions of all of the single gas laws as a part of the general gas law. Now, in the table on the left, if we start off with 20 cubic feet and we just examine the effect of temperature, that would be Charles' law, you can see the gas volume decreases as we cool it, moving from an original 20 cubic feet to about 15 cubic feet. Now, this principle of Charles' law is actually put into play every fall in kitchens all around the world. When people are doing home canning, what they're really doing is they're applying Charles' law to create a semi-vacuum state. They take a glass jar of tomatoes, for example, they seal it inside a boiling pot of water, and then they put it on the counter so that it cools. We refer to that as home canning, but what we're really doing is we're using Charles' law to create a vacuum seal. It's kind of like vacuum pack food. And with this low gas pressure, this reduced vacuum-like pressure, it's very hard for bacteria to replicate because they need to have a certain amount of gas pressure in order to ferment food. And so people know that the food lasts longer, and we call it home canning. Well, the physical law that makes that possible is Charles' law, as you can see in the top. Now, Boyle's law, of course, is pressure and volume. So if we look at this original 20 cubic feet and we examine what happens if we increase the pressure, you will notice moving down vertically that we also decrease the volume. If we look at the simultaneous effects of cooling and pressure, then we find the greatest change in volume. Moving diagonally, we start off with 20 cubic feet. As we compress and cool, we can drop that volume from 20 down to something as small as some 5 to 6 cubic feet, an enormous reduction. The final principle I would like to talk about here is Pascal's principle. Pascal's principle is the phenomena where a force applied to any part of a liquid is uniformly distributed throughout all of that liquid. Pascal's principle actually forms the basis of all of hydraulics and hydraulic engineering. The clinical importance of Pascal's principle is based on the fact that our body contains many fluids. The entire vascular system is liquid. And as we apply force to that liquid, it's uniformly distributed throughout that liquid. So here's a common question I'm oftentimes asked. If I have a patient with glaucoma, a disorder of the eye where there's an increased intraocular pressure, can I put that person in a hyperbaric chamber? Well, if you understand Pascal's principle, you'd know the answer is yes. Because as we put the person in the chamber, the concern for many people who don't know Pascal's principle is that if I increase the pressure on the eyeball, and they already have problems with high intraocular pressure, could that make things worse? Well, it might. However, Pascal's principle teaches us that the force applied to the surface of the body is transmitted to all the liquids. So as we apply force to the legs, for example, we increase the venous return to the heart, which increases the arterial pressure head, which increases the perfusion of the eye. So although I may increase the pressure on the surface of the eye, I've also correspondingly increased the perfusion pressure of the eye, and it's a net zero. So the answer is yes, these people can go into the hyperbaric chamber. And the same can be applied to other liquid or hydraulic scenarios. However, if one considers the difference of the pressure in the chamber to the difference of pressure outside the chamber, that's a very different scenario. I saw a rather dramatic illustration of that pressure difference. And it dealt with a patient who had an IV in. Later on in the operations session, you'll learn that we can provide intravenous therapy to our patients while they're receiving HBO. This is made possible because the IV bag on the outside can connect inside the chamber in what's called a through-port penetrator. You'll get a chance to look at that more closely later in the operations session. But for now, I just want you to understand Pascal's principle. So we start with a bag of fluid on the outside. It comes down through a hyperbaric pump that can pressurize that fluid sufficiently that it will now go into the high-pressure chamber and then into the patient. Now, what happened next is rather interesting. And before I tell you what I saw, let me pause for a minute to make an observation about venous bleeding and arterial bleeding. And you'll see why this is important in a moment. I'm sure many of you have seen venous bleeding. It sort of oozes. The amount of pressure driving that is only a few millimeters of mercury. Now, if you've ever cut a small skin artery, you've probably observed that you can get a fairly respectable arc of blood. So how much pressure is accountable for that? Well, if your diastolic pressure is 70 or 80 millimeters and your systolic is 140, you probably have a mean arterial pressure of around 100 and 110 millimeters that accounts for that very respectable arc of blood. So if 110 millimeters gives you a pretty respectable arc of blood, you can imagine what might occur if this IV became disconnected. Well, that is exactly what happened. I walked into a hyperbaric unit one morning. I glanced up at the ceiling. The whole thing is covered with blood. I asked the staff what happened. I said, "Oh, Dr. Bartlett, you should have been here last night." Well, what had happened is the patient was inside the hyperbaric chamber. The IV became disconnected outside the chamber. So the pressure differential across that IV at 2 atmospheres absolute, think about what we just learned, would be the patient's venous pressure, perhaps 3 or 4 millimeters of mercury, plus an additional atmosphere, 760 millimeters, which means they had a driving pressure of over 765 millimeters of mercury. Now, if 110 gives you a respectable arc of blood from an arterial bleed, can you imagine what happens with over 700 millimeters of pressure? Well, the end of the IV was now jet-propelled, flailing about the room, spray painting the ceiling. And although the staff was able to clean up everything else, they couldn't clean up the ceiling tiles because of the blood splattered all about them. So this is a rather dramatic illustration of Pascal's principle. Now, before any of you become alarmed, you should know that these IVs have a back check valve to prevent that very thing. Why this back check valve didn't work, I'll never know, because unfortunately the IV tubing had been discarded. But apparently there was a defect or a malfunction in the valve. Now, had that IV become disconnected inside the chamber, there would be no pressure differential, and then it simply would have oozed as any IV would do. But Pascal's principle, again, a very important concept here, and a rather dramatic illustration. So to summarize here, on this matter of physics, the concepts that we have looked at in this session. We have talked about this concept of pressure and come to realize that it can be expressed in many different ways. There's atmospheric pressure, hydrostatic pressure, and absolute pressure. There's also the concept of gauge pressure and partial pressure. Gauge pressure is very common in many hospital pressure gauges, and partial pressure will become very important as we begin to explore the physiologic properties of each of the component gases that make up this mixture we call air. That, of course, would be Dalton's law. As we come back and look at the gauges we looked at the beginning of this session, this is the gauge for a monoplace chamber. Those letters PSIG, although they may have been mysterious when you began the session, I bet you know what they mean now. That's right, pounds per square inch gauge. Well, how about the inner circle of that scale there? The 15 above, well, that is 15 pounds per square inch gauge. You may have also noticed that right beside that are two little dots, and they're just short, just shy of 15. Well, that would be 14.7. And that is to remind you that at 14.7 you have 2 atmospheres absolute. That's what the 2 dots are indicating. If you move to the right on the scale, you'll notice that there is 2.5 dots, and just short of 30 pounds, there is 3 dots to remind you that you are now at 3 ATA, or 3 atmospheres absolute. Well, how about those numbers on the outside of the gauge? Well, if you look closely, you notice it's expressed in kilograms, so that would be the metric scale. The manufacturers of these chambers ship these devices all over the world, and it would be far too difficult to create many different kinds of gauges. So what they do is they create one gauge that can be read many different ways. It's kind of like modern automobiles. If you wish to look at the speed in miles per hour, you can press a button. If you want to look at it in kilometers per hour, just press it again and you'll get your speed in kilometers. So this is what you're looking at when you're reading a monoplace gauge. Well, how about that multiplace gauge? Well, looking at that depth absolute, you now know that if the needle on this gauge read 33 feet of seawater, you are equivalent to 2 atmospheres absolute. Well, how about if the gauge read 45 feet of seawater? Well, that is equivalent to 2.5 atmospheres absolute. And of course, at 66 feet of seawater, you would be at 3 ATA, or 3 atmospheres absolute. Now, later on, when we talk about decompression tables, you'll have a much better appreciation as to why it is a multiplace chamber is calibrated in feet of seawater, as opposed to a monoplace chamber where the pressure is usually expressed in pounds per square inch, or atmospheres absolute. Now, the other concepts that we have looked at here in this session is the concept of temperature. And you can better appreciate why it is your patient's experiencing warming and cooling of the chamber. We also have looked at the gas laws, Dalton's law, the law of partial pressures, and later on we're going to look at certain gases in particular, oxygen and nitrogen, and Dalton's law becomes very important. Boyle's law, which is a relationship of pressure and volume. The clinical implications of Boyle's law are substantial, and we have an entire hour dedicated to barotrauma, which is specifically the clinical effects of Boyle's law in everyday practice. So you should look forward to hearing about that session later on. We also talked about Charles' law, which is the effects of volume in accordance to temperature, Gay-Lussac's, which is the effect of pressure in accordance with temperature, and then of course there's Henry's law, a very important law. I sometimes call that the soda pop law because that's the solubility of a gas in a liquid. And I'm sure that deep in the heart of Coca-Cola and Pepsi-Cola and any of the sparkling water companies, there's probably some engineer that knows everything about Henry's law, because Henry's law is what puts the sparkle in the sparkling water. Well, I hope you've enjoyed this session on physics. In the next session, we're going to look at the direct application of physics to the physiology and see how that begins to form the foundation for the clinical indications that you'll be talking about and looking at more closely later on here in the curriculum.